video demonstrates how a large language model, or LLM, interprets a prompt and turns it into a response. Each step links the technical process to what is happening inside the model using a typical workflow inside Microsoft Azure's AI playgrounds. Let's go to our Playgrounds interface in the top left navigation and open the Chat Playground. We'll create a new deployment since we haven't used this playground before. We'll search for one of the GPT models in the dialog box. Select a model and choose Confirm. Then select the Connect and Deploy button. The workflow begins when a prompt is entered into the input box in the lower right half of the screen. This walkthrough uses the Azure Playground environment, which provides easy access to LLMs such as GPT, a well-known language model made by OpenAI. The process of turning a prompt into a response involves 4 major steps: tokenization, embedding, running through a transformer architecture, and generating an output. Each step shapes how the final response is created. Step 1 is tokenization, which is the process of breaking down the input text into small units called tokens. Tokens are not always single words. They may be part of words or whole words, depending how the model is trained. For example, let's enter the sentence, "Tell me a story about space." This prompt is divided into tokens such as tell, me, a, story, about, space. Each of these tokens is a building block the model uses to process the message. Tokenization helps the model convert human text into a format that is easier to analyze and process. Each token is given a unique number that the model uses for computation, a process called encoding. Step 2 is embedding formation. Each token is changed into a set of numbers called an embedding. An embedding is a mathematical way to represent the meaning of a word, phrase, or token in a format the model understands. Tokens with similar meanings such as space and universe may be close together in this numeric space of embeddings. These embeddings help the model recognize patterns and relationships between words. Embeddings are essential because they allow the model to understand context and relationships among tokens, not just their direct meaning. This helps the model build more meaningful responses to prompts. Step 3 involves processing through the transformer architecture. Transformer is the type of neural network used by LLMs. This architecture handles the input tokens and their embeddings together using multiple layers. A core feature of the transformer is self-attention. Self-attention allows the model to focus on different parts of the input prompt, deciding which tokens are most important for producing a good response. For example, when the word space is used, the model looks at the surrounding words like story and decides how important space is in this context. This helps the response stay on topic and relevant to the original prompt. The transformer has many layers that repeat this process, each time refining the relationships and understanding between tokens. This step-by-step process is what enables LLMs to produce complex, detailed responses. Finally, in step 4, we generate the response by selecting this blue arrow at the bottom right of the screen. Generating takes all the processed information and selects the most likely next token, one at a time until a full reply is ready. This process repeats quickly, finishing the complete response you see on the screen. For the demonstration prompt, "Tell me a story about space," the model might respond with a short creative story that uses the information encoded in the embeddings and processed through transformers. The quality and detail of the response also depend on the model settings such as temperature and maximum tokens. You can find these settings inside the parameters dropdown on the left. Temperature located here changes how varied a response is. A low temperature makes answers more predictable, and a higher temperature adds variety. Max response sets a limit on the length of the response. Large language models process tokens simultaneously, not in order like earlier systems, such as recurrent neural networks or RNNs. This means transformers are much faster and more efficient at handling information, allowing them to generate text more quickly and with better context. As we've seen, the process moves from human text to tokens, to embeddings through the transformer, and finally onto a detailed context-aware response. Each stage builds on the last, making the final answer possible.